that was essentially breaking symmetry, because the symmetry of the theory naively suggested that there could be no mass for this. If you did perturbation theory, you would not normally see a mass. But perturbation theory in itself was very worrying, because you could do first order, then you start working up to higher orders, and this thing was horribly divergent, and there was no way, using the rules of renormalization, to make this thing finite. And that was all the more of concern and links into this talk, because of course at that time the weak interactions were described by 4 fermion interactions. It was an easy way to describe neutron decay, for example, and many other things. And what Nambu did with Jan Lucinio was develop a new leading order approximation for this theory, which had a non-zero induced mass, and in fact, as a consequence of that, the symmetry by the symmetry breaking, meant that the vacuum was not invariant under the chiral current, that was chiral charge, which was supposed to be conserved, and the price you paid for it was that a massless particle was induced. A massless particle was called the Goldstone boson, or the Nambu Goldstone boson, and it was studied carefully in a scalar field theory by Jeffrey Goldstone. Now, as I said, little was understood beyond coupling constant perturbation theory. But it was already clear, if you looked in the literature, that there was going to be a fundamental problem with coupling constant perturbation theory for E and M, or in fact in general, and that you could not expect the perturbation expansion on general terms to be a convergent expansion. And in fact, Dyson showed that you could expect a coupling, a singularity at zero coupling in QED, and that in turn suggested that the perturbation expansion at best was asymptotic. You start going to higher and higher orders of perturbation theory, and you start going away from your answer. It was not a Taylor expansion. Now, in retrospect, that shouldn't be surprising. We weren't very sophisticated at the time. But if you look at the simplest possible field theory you can think of, the field theory of zero space-time dimensions, so there's no kinetic term, and you put down a simple interaction, and in particular if you put down a quartic interaction like phi to the fourth, and if you write down a Lagrangian, and you produce the field equations, you get a simple differential equation. Here, J is a source, something that you vary by hand outside. Now, this is a differential equation which you can solve, right? It's a linear differential equation. And right away when you look at it, as you solve it, how many solutions does it have? Well, every freshman knows that, or at least they used to, right? It has 3 solutions in general, because it's a third order differential equation. And if you write it down, if you write down an integral representation for it, it looks like a path integral, except there's no kinetic energy. You can look at this particular path integral. You see it has 3 stationary phase points, and you can expand around those stationary points to produce the 3 solutions, or just solve the differential equation if you want. The stationary phase points are located at phi, which is ddj of z, at phi equals 0, or at 2 points which are not 0. Now, in particular, if phi isn't equal to 0, that is what corresponds to symmetry breaking if you're looking at normal theory. And in fact, what it does, the original action for this theory in 0 dimensions is reflection invariant. But these 2 extra solutions that are shown are not reflection invariant. And this already, this is the simplest possible thing you can think of, right? This isn't really a field theory, it's differential equations. But you build a field theory by putting together lots of points and put degrees of freedoms at the point, and somehow or other they should reflect this underlying structure. In fact, they do, but in a very complicated way. You get lines of singularities. They form together to form branch lines. You get phase structure, and all this is very interesting and very hard to explicitly construct in general. But the information was already there if we looked at field theory in that simple form. You could not expect there to be only one solution. There are other solutions, and explicitly, as is hinted at, or you could see by solving that equation, since there was a coupling constant, G, in front of the third derivative, all the other solutions to that differential equation, aside from the phi equals 0, 1, are singular as the coupling goes to 0. What does that mean? It means there's no perturbation expansion, not around phi equals 0, because the leading order term is singular. Okay, so in general, you could expect, when you look for solutions beyond perturbation theory in quantum field theory, you would find solutions which are not perturbative. That is, that they don't have a nice coupling constant goes to 0 limit, and in fact that they're likely to be symmetry. In fact, they must be symmetry breaking. So now going on, if we increase the degrees of freedom, you can to go to, say, 4 dimensions and look at theories that apparently have conserved current, say the same theory, phi to the 4th. Put in a rotational symmetry, something that looks like charge, then there's associated with that charge, you would normally expect that the expectation value of all the fields in that theory were non-vanishing, but in fact you can force them to be would be vanishing, but you can force them to be non-vanishing, and then there is a thing that called Goldstone's theorem that says if you break the symmetry in a relativistic theory, you're going to have a 0 mass particle. Now, this is a problem, because what are the 0 mass particles? Well, the photon, right? That's one 0 mass particle that we know about. And that's very interesting. And I was a graduate student at Harvard, and Derek Kane came to give a talk, and he talked about a model which was a generalization, or a different version of the Nambu-Yano-Lucidio model, which was a coupling of 4 fermions through an interaction that made it look like the coupling of 2 currents, beginning to look a little bit like weak interactions. In fact, maybe there was a hint there. And he said, well, let's break the symmetry of this model, so we'll require that the expectation in the state of lowest energy of the currents was non-vanishing. Now that's a little worrisome, right, because the current carries a vector index. And in fact, what you're doing is that you're breaking Lorentz invariance. My advisor said, when you take a look at this just can't be right. You don't really want to break Lorentz invariance. And so I worked through it, and you know, as he always is, to the first and the important approximation, Kane was right. Some of the details were wrong, but it turns out you break the